Okay, there we go. We're recording. Welcome to Thursday's lecture, and we're going to pick up where we left off yesterday. So we left off, we technically finished all of the content and concepts and material from geometric optics, and now we're just left having to practice a little bit. So we left, the very, very last thing we left off with yesterday was double lens systems, and we can do some example problems with a double lens system. So we'll do one of those now just to both refresh ourselves with ray diagrams, the thin lens equation, and also how to apply those two things in the context of a double lens system. And I've put together some summaries and other practice questions in optics as well that we can do before moving on to the next chapter. Okay, so let's do this before too much time goes by. So panel A shows a jalapeno seed labeled as O1 that is placed in front of two thin symmetrical coaxial lenses, lenses 1 and 2, with focal lengths of positive 24 centimeters and positive 9 centimeters respectively, with the lens separation of 10 centimeters. So they're 10 centimeters away from one another. Both of the focal lengths are positive, which means they're both converging lenses. They're both convex lenses. And the seed is known to be 6 centimeters away from lens 1. Where does the system of the two lenses produce the image of the seed? So step one is what I would say personally, just because of scientists and words. I would personally just start by writing the information out from the statement of the question, and then that way your brain and your eyes can just very specifically see the givens. And then after that's done, then we'll move on to the actual analysis. So I'm just going to reread this and pull out all the information from the text. So we have focal length 1 is going to be positive 24 centimeters. We have focal length 2 is going to be 9 centimeters. We have a lens separation of 10 centimeters. And the seed is 6 centimeters away from lens 1. So the distance of the object is 6 centimeters. And we want to know where the image is. Of the entire system, not the image of just the first lens, the image of the entire system. Okay, now I am going to start analyzing this. So we recognize that this is a two-lens system. And if you recall from our discussion yesterday, we were saying with a two-lens system, quite simply, you just analyze one lens at a time. And the output of one lens will be the input for the other lens. So let's start here by drawing the first lens. So we'll call this lens 1. And we're going to ignore the second lens momentarily, because that's what we do. We just propagate the first lens first. So here we're going to have object, the jalapeno seed. For some reason they call that O1. They should have called it like J1 for jalapeno seed. Even that would have made more sense than like capital L for angular momentum, because at least jalapeno starts with a J, even though it doesn't sound like it starts with a J. But anyway, they're calling it O1, so let's call it O1. Now we know that this has a DI value that's known. Sorry, not DI, sorry, DO value. A DO value that's known, it's 6 centimeters. We also know the focal length is 24 centimeters. So the focal length will be somewhere over here, focal 1. So in this case, the object is closer to the lens than the focal point is. So if you recall, just to pause for a second, just to review, if you have an object that's closer than the focal, then you're going to get a virtual erect image that's larger than the object on the same side of the lens, not on the opposite side of the lens, on the same side of the lens. So that's just a bit of a concept for you. Okay, now even if you didn't see that, you could just mathematically figure that out using the thin lens equation, but it's always good to sort of have an understanding of what the answer kind of roughly should be ahead of time. It's what we call a sanity check. It's to make sure that you didn't forget a negative sign somewhere or something like that. Okay, so we propagate it. We want to know where everything is going to be. So we set up our thin lens equation. So it's going to be 1 over dO plus 1, oh, not d, 1 over di equals 1 over focal 1. And we have focal 1. We have dO, so the only thing we need is di. So let's go about solving for di. It's going to be 1 over focal 1 minus 1 over dO. And this is going to be 1 over, what's focal 1? 24. And dO was 6. Oh, look, it's not a coincidence that 6 is a multiple of 24. I'm sure that was done on purpose. So 6 times 4 is 24. And motoring right along, we're going to get -3 in the numerator, 24 in the denominator. So that makes the distance of the image at 24 over -3, which is going to be -8 centimeters. Now, what does it mean for it to be at -8 centimeters? Well, the fact that it's negative by our sign convention means it's a virtual image. And for a converging lens, in order to have a virtual image, then the image has to be on the same side as the object. Because with a converging lens, the light rays start or originate at the object, and then they pass through the lens, and they continue on the other side of the lens. So the light rays are physically traveling through the lens and beyond. So the light rays do not in any way reflect backwards and come back on the same side of the lens. So the fact that we have a negative answer means it's virtual. And in the context of this, virtual means same side as the object. So if this was 6, then our answer here is going to be distance of the image is going to be -8, which means negative is on the same side as the image in this specific case, and it's going to be at 8 centimeters. So this is going to be maybe green, blue, black. I'll just say black. This is going to be di, and it's going to be 8 centimeters. Okay, so that's going to be O1 prime. Now, if you wanted to, you could calculate its height as well with the magnification equation. I don't think they're actually asking for that, but let's double check. Where does the system of the two lenses produce the image of the seed? So they're just looking for location. They're not looking for magnification. However, just for enriching purposes, if we were looking for magnification, you could say the magnification was equal to hi ho di-do with a negative sign, you know. And from here we have everything we need. We have, I think we have the height of the seed. Do we not? Oh, we don't have the height of the seed. So maybe we don't have, no, we don't have the height of the seed. So we don't have enough information for that. We would need to at least know the height of the seed or the height of the object. You would say the height of the image would be minus di over do times ho. So we would have di, we would have do, but we would need to be told what ho is, which we aren't. So I guess that's why they don't ask for it. All right, so anyway, what am I saying? I'm saying two lens systems, you just treat one lens at a time. We've done the first lens, so now, oh, let's maybe perhaps keep the same color. Let's do the second lens. Lens number 2. Well, this is where we have to make sure our diagram is correct. We are told that lens 2 is 10 centimeters to the right of lens 1. So we know this was 10 centimeters, and this was the location of lens 1. Now we're ignoring lens 1 for a second because we've already propagated that. We've already studied lens 1, but I'm just trying to make sure my distances are correct. And we also know that the distance of the image is 8 centimeters to the left of lens 1 even. So we know that this is going to be 8 centimeters, and this is going to be where O prime is. Okay, so I'm only drawing a diagram here to make sure all of my distances are correct. So here's the trick, as I said before. Lens 2, all lens 2 is able to quote unquote see, and I mean, I don't even need to use quotes here because seeing is about light rays hitting your eye, and there are light rays coming from object prime, O prime, going into lens 2. So I guess if I want to personify an inanimate object, this is the closest, most accurate way to do so, because this is actually physically what seeing is. So all lens 2 sees is lens 2 will see this image 18 centimeters away from the lens. So in this situation, you would say the distance of the object is actually 18 centimeters. The focal point for F2 is 9 centimeters. And again, you know you're kind of doing this correct because look at the numbers, 18, 9, they're multiples of each other. I know in real life they could be not nice numbers, but in a textbook setting, you know, we usually try to make the numbers nice enough that you don't really need complicated calculators. So the mere fact that we're getting multiples of each other tells me we're kind of on the right track, more of a psychological insight into how to approach physics problems in academia. Anyway, that aside. And what are we looking for? We're looking for the distance of the image. We want to know the location of where the image of the second lens is going to be. And again, we just apply the thin lens equation. Just instead of with values from the first lens, the values from the second lens. So DO is going to be, well, let's rearrange first. I don't want to plug in values. Let's rearrange first. So 1 over DI is going to be 1 over F2 minus 1 over DO. And solving 1 over, what was that, 9 minus 1 over 18 equals 1 over DI. I think that was right. F2 is 9, DO is 18. Yep, cool. And going through this is going to be 1 over 18, I believe, because we're going to be doing 2 over 2. So 2 minus 1 is 1 over 18. So this means the distance of the image is going to be at 18 centimeters. And it's going to be, it's a positive value. So a positive value means it's inverted. Sorry, a positive value means it's real. Sorry, it means it's real. What does it mean to be a real image for a converging lens? Well, we've looked at lots of those ray diagrams in the past. So let me just make a little note here. I'll say DI is positive, meaning, oh, that's a terrible M, meaning it's real. So if we scroll up here, what does it mean to have a real image for a converging lens? Where are we here? So let me just erase all of my pen markings here to make it easier for you to see. So what does it mean to have a real image for a converging lens? Well, here's a summary of the converging lenses. And all of the cases that have a real image is going to be case A, case B, and case C. Case D, E, and F all have virtual images. So in every single case, as you can see, with a converging lens, a real image is always on the other side, and it's always inverted. So we know from context, we do know it's a converging lens because it's got a positive focal length. And if it's a real image, we know it's on the other side of the lens, and it's going to be inverted. So that means the image is going to be at DI equals 18 centimeters, and it's going to be inverted. So somewhere down there. So it depends kind of how they want us to answer the question, because distances are involved, and distance is relative to a point. So we could say it's 18 centimeters to the right of lens number 2. We could say it's 28 centimeters to the right of lens number 1. We could say that it's, where was the initial location? The initial location was what, at 6 centimeters, I think? Yeah, 6 centimeters. So 28 plus 6, we could say it's 34 centimeters to the right of the seed, the real seed. So it really depends what they're asking for. They're all correct. It's arbitrary. So we could say, therefore, the image is 18 centimeters to the right of lens number 2, or, of is not FO, of the right of, oh no, that's 2. Okay, sorry, 2 to the right. Or we could say the image is 28 centimeters to the right of lens number 1. Either one is correct. Or we can even say something like a third thing. We could say the image is 34 centimeters in front, or to the right in front of the object. Whichever one. You by no means have to say all 3, of course not. You don't have to give us every possible frame of reference in your answer, as long as you give us a valid frame of reference and distance combination. Of course, you know, that's totally fine. So what do they say here? They say, okay, they're giving you 18 centimeters. So the answer that the slide is giving us is in reference to lens number 2, which is fine. I mean, it's one of the correct interpretations. Okay, so anyway, that is an example of a 2-lens system. As I said, they're really not that much more challenging in any way than a regular lens. A regular lens, you're just sort of doing it once. A second lens just means you're doing it twice. Okay, it's nothing more challenging than that. Now, a fun little tidbit, you know, you might think to yourself, oh, well, if it doesn't really add anything, it just means you're doing it twice, then why bother doing it? Well, if you think about it, the distance between the 2 lenses, presumably that's something you can change. You know, you can put it on a track and you can slide them. And this is how telescopes are made, and binoculars, and you know, microscopes and cameras. You know, when you have cameras, you know, when you zoom a camera, you can see the little protruding, well, the lens of the camera, but the protruding part of the camera. When you're zooming in, you see the lens move in and out. And what you're doing there is you're changing the distance between the 2 lenses, and you're changing the overall magnification of the overall system. So that's how you can zoom in and zoom out, and, you know, without having to physically walk closer to the object. So, you know, manipulating these distances is actually useful. You know, it's not something we just do because we can. It's not something that we throw in the curriculum because we can. This really is that a 2-lens system is really the basis of Zoom. Not the platform we're on, but Zoom on a camera. It's also the basis of a telescope. You know, it's how we can sort of look at stars from really far away. Again, you're playing with that sort of magnification. So you can sort of use, I mean, presumably if you had a lens that was able to magnify everything in one shot, then sure, but then you'd be carrying a lot of lenses around with you, because each lens would have its own magnification, right? So, you know, you'd have to be carrying around a big briefcase of lenses and swapping them out for exactly the location, you know, for the distance of the object that you're standing in front of. You know, when you have a 2-lens system, that you allow them to move relative to each other, You can change the position of the image. You can put things in focus. You can magnify them. And then that way you're not having to carry around a whole briefcase full of different lenses. So, you know, it allows for more flexibility and a wider range of use of that equipment. So that's why we do it. It's not just to torture students because it's something that we can torture students with. It's something that is very practical in real life. Okay, so what I've done is I have prepped a sort of summary of all the ray diagrams and some more practice questions. So before we move on to the wave nature of light, I would like to just sort of do a bit of a summary recap and then some practice problems. So here is, I have to scroll up. I don't know why it keeps going in the middle. So here's a summary of all the ray diagrams for you. So for a concave mirror, because that's where we started, don't forget, we started with mirrors. So here are the scenarios. You have an object that is beyond the radius of curvature, or what we call the center of curvature. If you have an object beyond the radius of curvature, you are going to get an image that is somewhere between 2f and f, somewhere between the focal and the center of curvature, always. Now, as the candle moves farther away, the location of the image will move closer to the focal. And as the candle moves toward the center of curvature, the image will move closer to the center of curvature as well. But that's why it says the distance of the image is somewhere between C and F. The orientation will always be inverted, which means M, the magnification, will be negative, and the image will always be smaller than the object. So the magnitude of M will be less than 1. So these are sort of patterns that you can sort of predict, conceptual patterns that you can predict. And then if we move the object, same scenario, concave spherical mirror, if you move the object onto the center of curvature, or at what we call the radius of curvature, then the image is going to be located at the radius of curvature, so at the same location, but just upside down. The orientation is inverted and is negative, but the magnitude of the magnification is exactly equal to 1, which means it's not bigger and it's not smaller. Now, interestingly enough, there is a place in San Francisco, it's called the Exploratorium. And I've been there twice, I want to say, maybe 3 times. And it is by far my favorite place. I've been to Disney, I've traveled, I've been to Europe, and I can honestly say, and out of all the places I've been, the Exploratorium has probably been hands down my most favorite place. It is it's like the Ontario Science Center, but actually good. It's an entire science center, if you will, full, huge, it's massive, and it's all full of like really cool physics demos. And they've made physics really fun. They have physics demos from, you know, classical motion down to, you know, fluids. They have demos with electromagnetism. They have demos with optics. It's all really super cool. And one of the demos they have is they have like a coil or a spring that is mounted upside down out of sight. And they have a mirror behind it. And the image of the mirror is a spring or an object that is inverted. So if the object itself is upside down, then the image will be right side up. And it looks plain as day. You look at it and it looks crisp, it looks sharp, it looks clear. And then there's a little box for your hand to go in, and you could try to grab it and your hand goes right through it. It's literally, it looks phenomenal. It looks like a hologram almost. It looks so sharp, it looks so real, and you go to grab it and your hand goes right through it because your eyes are looking at the image and the object is conveniently out of sight. So it's really cool. If anyone has a chance to go to San Francisco, I would highly, 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 highly recommend going to the Exploratorium. It's just so very cool. Anyway, I digress. Moving on. So again, concave mirror. If you continue to move the object, and if you move the object closer than the center of curvature. So somewhere between r, the radius, the center, and the focal, then again, you're going to get a real image. It's going to be inverted. So you're noticing a pattern here. There's like most of the time there's a real inverted image. However, now once the object has crossed the threshold of the radius of curvature, then the image is going to be farther behind the radius of curvature, and it's going to be larger than the object. So there's actually going to be a magnification larger than 1, but it's still negative because it's still inverted. And then the next milestone in our growth is to put the candle at the focal. And you might recall me saying, you know, this is how we create a spotlight on a stage. So this is a spotlight on stage, for instance. You put a light source at the focal point, and the light rays will come out parallel. So there will be no image. So the mathematically, the location of the image is at infinity, which means it's not even virtual, it's not even real, it just doesn't exist. The orientation is not applicable, the magnification is not applicable, so we can't even talk about those. And then the last scenario, I guess, scenario 5, for a concave converging mirror is when you place the object closer to the mirror than its focal length. And this is the only scenario in which we have a virtual image, and it just so happens that it's also upright, it's not inverted. So if you have a spherical mirror and you have a virtual image, you can be guaranteed that it's going to be upright and larger. Vice versa is also true. If you're told that you have, an erect image that's not inverted, you immediately know, if it's a concave mirror, you immediately know it's going to have to be virtual, because it's the only case where you have an image that's not inverted. So here's just a slide with all of those diagrams kind of on the same slide, so you can kind of, your brain can see them all at once here. So please, when you're studying this or reviewing this, you can go back and you can sort of look at the pattern of where the object is versus where the image is, and as a function of location. So it helps you to become more familiar with kind of how to think about these concepts. Now, we had like multiple slides for the concave mirror. Concave mirror. We're only going to have one slide for the convex mirror, because the convex mirror, although the ray diagrams are the same, in parallel out through the focal, and through the focal out parallel, and the equation is the same, really what makes this one so much simpler is that it's always a virtual image. For a convex mirror, a diverging mirror, you never get a real image, ever, which is kind of really cool. So we can sort of summarize all of the different cases on the same slide. It doesn't matter where the object is, whether it's at F, or whether it's at 2F, or whether it's beyond the center of curvature. It doesn't matter. You're always going to get a virtual image, and it's always going to be erect, and it's always going to be smaller. It doesn't matter where you are, the answer is always the same. So this sort of shows you, even if you're really close, you're still going to get a virtual image, and it's going to be erect and smaller. And even if you're really far, it's going to be a virtual image, and it's going to be erect and smaller. So there you go. It's all the math and all the concepts are the same, but because of that negative sign in the focal length, because don't forget this will have a negative focal length. Because of the negative focal length, the distance of the image will always be negative. So that simplifies the number of different cases that we have to look at. Okay, then we moved on to lenses. So with lenses, we're going to do something similar that we did with the converging mirror as we did with the converging lens. So the lens, instead of calling it a concave mirror, we're calling it a convex lens, because the convex lens is what converges, whereas a concave mirror is what converges. So here again, we're going to have similar patterns. If you have the object placed beyond the center of curvature or the radius of curvature, then you're going to get an image, a real image that's inverted and smaller in between f and 2f, or f and the radius of curvature. This is the same values or pattern as case 1 of the concave mirror. Okay, so it's not like having to memorize 2 separate things. And well, frankly, you shouldn't be memorizing anything, but you know, if you're trying to get things sorted out in your head, it's not like you're trying to sort out 4 different things. I mean, the concave mirror has the same pattern as the convex lens, right? So once you understand how to manipulate and think about one pattern, you've got 2 different cases under your belt inherently. Same thing here. You put the object at the radius of curvature or the center of curvature. Those 2 words are synonyms in this context. And your result is going to be at 2f. Your image is going to be at the radius of curvature. It's going to be real. It's going to be inverted. And the magnification is going to be 1. It's not going to be bigger. It's not going to be smaller. And the same pattern holds for case 3. If you put the object sort of in between the center of curvature and the focal point, your answer is going to be beyond the center of curvature. It's going to be beyond 2f, and it's still going to be inverted, and but this time it's going to be magnified. It's going to be larger than it was originally. So the magnitude of m is going to be bigger than 1, but m is negative because it's inverted. And same pattern happens with case 4. If you're at the focal, nothing happens. There is no image one way or the other. It's not virtual, it's not real, it just doesn't exist. And then last but not least, with a converging lens, if you put the object closer to the lens than the focal is, then you're going to get a virtual image. And this is actually how a magnifying glass sort of works. This is sort of how a magnifying glass works. And if you have a magnifying glass laying around at your house, try it yourself. If you hold the magnifying glass up and try to look at something kind of far away, you'll notice it looks blurry and upside down. Well, that's because the object you're looking at is beyond the focal. A magnifying glass will only magnify if you place the object closer than the focal length of the magnifying glass. So if you want, if you do have a magnifying glass laying around at your house, that's, I don't know, depends on your parents, I suppose. Magnifying glasses are becoming a thing of the past, but if you do have one laying around your house, you can figure out where the focal point of the magnifying glass is by looking at an object, you know, putting an object really close up to it so it becomes enlarged and clear, and then you can slowly pull the magnifying glass away, and as soon as the object becomes like very blurry, and it'll happen pretty quick. It'll look like in focus, in focus, in focus, and then out of nowhere it'll just disappear. And when it disappears, you're going to be in this case here. When that object becomes sharp, 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 and then disappears, that object will be sitting at the focal point of your magnifying glass. So that's an easy way to, and you can measure that, you know, a relative, sibling, parent, whatever, they can come in, you can hold the magnifying glass at that point, and then someone can come in with a ruler, and then they can measure that distance. Come to think of it, that'd be a fun lab to do in person, but unfortunately, we don't have that luxury this summer. Anyway, so here is a sort of summary of all of those arrows in one diagram for you, so you can sort of see the mapping. So if you place an object kind of beyond, well beyond the radius of curvature, then it's going to be small and closer to the focal. If you place it at the radius of curvature, it's going to be at the radius of curvature but inverted, and then so on and so forth. You can see the mapping there. And then the last but not least, we have the concave lens. Again, the ray diagram is very similar. We go in parallel and then out as if it's through the focal, boop, right? And Then the other one is we're going to be going in through the focal and we're going to be coming out parallel, something like that. So here, anywhere, same thing with the diverging mirror, the convex mirror. It doesn't matter where you place the object. You can place it anywhere. You can place it at the focal. You can place it beyond the focal. You can place it closer than the focal, at the radius of curvature, beyond the radius of curvature, literally anywhere. Always, 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 your image is going to be virtual. So your DI value is going to be negative, and the image is always going to be formed closer than the focal point. And it's virtual, so if you put a screen there, you're not going to be able to see it. It's an optical illusion, so the only way for you to see the image is for your eyes to be looking on this side over here, and it's an optical illusion. Your eyes will your brain will inherently trace back the rays, and your brain will be tricked into thinking the object is actually there. So it's a virtual image, that's not a real image. If you put a screen there, it's not going to be anything. But if your brain is looking from the other side, that is what your brain will see. Okay, and just to summarize, these are the equations. There's really only 2 equations in this chapter. Even if it's a 2-lens system, it's just these equations twice. So hopefully this is a fairly, I don't want to say easy, I don't want to mislead you into thinking it should be easy, and then I don't want you to feel bad if you go to study and you're struggling with the questions, because they're not necessarily easy. I'm not trying to say that they're easy, but compared to other chapters where there's multiple concepts going on, halfway through you have to invoke momentum, or you have to invoke conservation of energy and then jump back to, magnetism or what have you. Those are a little bit more involved. They're multi-concept, multi-chapter. These are simpler in the sense that you're not necessarily like having to bring in momentum into this as well, right? It's just 2 equations really is all that's going on here. Okay, so let's do some practice. That really should have been in the practice thing here. Actually, before we do some practice, I'm going to open the chat for a second, because I want to make sure I address any questions you might have before we go on to do some practice. So now's your time before we jump into some more practice for lenses and mirrors. If you have any outstanding questions, then now's your time to ask them. Okay, so I'm not seeing any questions come through. I just want to make sure we're all sort of, if there's an outstanding question, I want to make sure everything is sort of addressed before we practice. Now, you might think of other things as we practice. That's very possible as well. Okay, I'm not seeing anything come through. So without further ado, let's do some lens practice, or optics practice. They don't have to be lenses. So here, this is just a reflection question. The figure below shows light reflecting from 2 perpendicular reflecting surfaces A and B. Find the angle between the incoming ray and the outgoing ray, R prime. Well, they're parallel, as you can see. It's at a 90-degree angle. So conceptually, you see that they should be parallel. Now, you can try to prove it using the law of reflection. So it's one thing to have a good intuition as to what you think is going to happen conceptually. Absolutely crucial. I'm not downplaying that intuition. I'm just making sure that you see kind of that this is not something that is just proof by trust me. It's something that you can actually use fundamental principles in physics to show. So the law of reflection, we know that theta in is going to equal theta out. So this is going to equal theta here. This is going to equal, by geometry, this is going to equal 90 minus theta, right? Because we know altogether that's going to be a 90-degree angle. So if that's theta, the other one's 90 minus theta, which means this is theta, which means this is theta, and that means this is 90 minus theta in here. So you can see here that with ray 1, maybe green, this ray 1 comes in at theta degrees to the horizontal. Or you could say at 90 minus theta with respect to the vertical. I don't care. Again, frame of reference, whatever floats your boat. So ray 1 comes in at theta degrees with respect to the horizontal. So if our frame of reference is the horizontal, we can look at the direction of r prime also with respect to the horizontal. So with respect to the horizontal, we see here that it is at an angle of theta as well. So that proves that it comes in at angle theta, reflects through a bunch of mirrors, and will come out at angle theta as well. Now, why is this true? Yes, I mean, principle of reflection, theta in equals theta out. But specifically, why is r parallel to r prime? Because the mirrors are at 90 degrees to each other. If they were not at 90 degrees to each other, the light would not be parallel. The reflected light, that is, would not be parallel. So it's because the mirrors are at 90 degrees to each other. Okay, let's make this a little bit more challenging. In the figure below, a ray of light is incident perpendicular to the face AB, so the face AB of glass, of the glass prism. So we're telling you that the glass is 1.52, index of refraction 1.52. Find the largest value for the angle phi so that the ray is totally reflected at the face AC if the prism is immersed in both air and water. So if we do A, we will inherently be able to do B. So what's happening here is we have a light ray that is going from either air or water, doesn't really matter, into glass. Now, when it travels into a new medium, it has the potential to refract. Now, it refracts according to Snell's law. Here, it's incident at 90 degrees. So that means it will actually pass through unbent because it's incident at 90 degrees. Sine of 90 is 1, so there's no bending. So it'll come in straight, and it will strike the hypotenuse here. And the goal is we want it to totally, there we go, totally reflect. So remember we talked about total internal reflection yesterday. So our goal is to have it come in and then bounce backwards completely. Now, the law of reflection is still true. So that means theta in is going to equal theta out. Now, I wrote that in the wrong spot. All of our math, Snell's law, they always measure angle with respect to the vertical or the normal. So here's the black dotted line here is going to be the normal to the surface. And so here is going to be theta in is going to equal theta out. We know this is true because of the law of reflection. And then we need to move to Snell's law to kind of figure out how to move forward from there. Now, what are they? They're asking about phi. I've labeled it theta. So what is theta's relationship to phi, or phi's relationship to theta? That's really what we're going to have to figure out here. Well, yeah, that's what we're going to have to figure out here. For now, though, let's solve for theta, and then we can relate theta to phi as we need to. So here, let's see here. What are we doing? Let's do Snell's law. N1 sine theta 1 equals N2 sine theta 2. So N1 is glass, And N2 is either going to be air or water, depending on whether you're doing part A or part B. So just to recap here, this is either air or water. And this is the glass here. So N1 is the material 1. It's where the light is coming from. So at the surface here, it's coming from glass. And N2 is going to be the material that it wants to go into. So it wants to go into either air or water. Now we're trying to figure out total internal reflection. So we set this to be 90. Right, that's our goal. Our goal is to make this completely come back in, not refract through. So we make this 90. So then we say, okay, sine of theta incident is going to be N2 over N1, and thus theta incident, which is actually in this case the critical angle, is going to be the arc sine of N2 over N1. Okay, so we've now solved for the required incident angle. Now, the incident angle is one thing. It's not necessarily a physical angle in terms of the prism. We want to know, how do we cut the prism? And of course, if we cut the prism on a steeper hypotenuse or a more shallow hypotenuse, that will definitely affect the angle at which a horizontal light ray is incident at. So we need to figure out that relationship. So for that, we can make a diagram or a better diagram. So here, well, it might be easier to use the one that they already have here because I have messy writing and this was generated by a computer. So we may as well use this one here. So here's the normal. There's the normal there. And this is what we solved for. That's the critical angle. So we need to figure out what the critical angle is in regards to the phi. So we see here that it makes a right triangle. That this is going to be, well, this is normal. So we know that's a right angle, that's a right angle. So there's 3 angles in there. And one of the angles is 90. So that makes the sum of phi plus theta equal to 90, because the 3 angles is 180 and one of the 3 angles is a right angle. It's already 90. So that means that theta is going to equal 90 minus phi. So here, we say theta is going to equal 90 minus phi. That's going to equal the arc sine of N2 over N1. And then solving for phi is going to be 90 minus the arc sine of N2 minus N1. So there you go. And again, we've inherently done A and B together because N1 is just 1.52, I believe. Yep, N1 is glass. And N2 is either going to be air is 1, or water, and water has an index of refraction of 1.33, if you remember from before. Okay. Next question. We'll do a few more and then we'll move on to the wave nature of light. In the figure below, a 2-meter long vertical pole extends from the bottom of a swimming pool to a point 55 centimeters above the water. Sunlight is incident on the surface of the pool at an angle of 55 degrees. I guess that's, well, it'll be before noon, presumably, because noon it's kind of at the highest point, so it should be coming straight down. So if it's before noon, it'll be coming in on a bit of an angle. Anyway, what is the length of the shadow? Oh, also, this is actually really good. I didn't realize this when I picked the question. This is actually kind of how sundials work. You know, when you work with shadows, they design the sundial, and of course they position it location-wise, but they designed the sundial to have a little sort of fin to cast a shadow at the correct temporal location, I guess temporal according to the face of a clock, based on the time of day. So the shadow is mimicking that of a clock, and it is pretty much the same premise here. At a certain time of day, the angle of incidence of the sun rays will be at a certain angle, in this case 55 degrees, and then the shadow will be at a certain location, and they've just mapped it. They said, okay, well, at this location we know it's just before noon, and then that's kind of how sundials were kind of invented. So very similar setup, which is kind of fun. Anyway, back to the question. So there's incident rays at 55 degrees. What is the length of the shadow of the pole on the bottom of the pool? And this is a little bit of a wrinkle because the light rays are hitting the water and then refracting inwards. So that's something to consider as well. So here, let's just draw a picture. Well, I should draw the pole as black. I should draw the pool as blue because duh. Okay, so there's the water in the pool. And sun rays are yellow, but I don't have yellow, because even if I did, you wouldn't be able to see it. So anyway, the sun rays that hit here, they're moot. They're really not of consequence because they're going to hit the pole and then stop, or get reflected into our eyes, and we're like, hey, look, there's the pole. The question though is, what causes the shadow? What causes the shadow is that the object blocks a lot of the sun rays, but at the top of the object, there's the first sun ray that's going to make it through, and then it's going to refract into the water downwards. And you see here that it refracts toward the normal. It bends towards the normal because water has a larger index of refraction of air. The speed of light is slower in water compared to the speed of light in air. And this is what will appear to be the shadow of the pole. Oh, I'm writing too close to the bottom of the screen. Shadow of the pole. Okay, so that's what causes the shadow. What causes the shadow is the absence of a light ray. Now, we've pretty much drawn our picture. Now it's all about geometry. We have to kind of figure out the geometry of the problem. So there's going to be Snell's law, obviously, in here. Now, in addition to Snell's law, oh boy, I'm deleting too many things. Okay, and then I need, okay, the water surface. So let's draw some of the distances. So it's a 2-meter long vertical pole, extends from the bottom of a swimming pool to a point 50 centimeters above the water. Okay, so this is 50 centimeters. This inherently will be 150 centimeters. So we know that distance. And this is not quite a nice triangle because the hypotenuse is partially bent halfway through. So we're going to need some geometry later on. So let's keep going. Let us figure out well, how much bending is going on. So let's just do Snell's law because we can predict we're going to need Snell's law at some point. Instead of saying 1, let me say air, sine theta air equals n water, sine theta water. Okay, so we have NA, it's 1. We have NW, it's 1.33. We have the angle of incidence. It's 55 degrees. So we have this, we have this, we have this. So we can actually find theta W, and that's just going to be a rearrangement of Snell's law. So N air sine theta air over N water. Now N air is 1, so I don't have to write that anymore. So I'll say theta water is going to be equal to the arc sine of sine theta air over n water. There you go. And then we can calculate the bending. Oh, wait, hold on, sorry. It's 55 degrees to the horizontal. Sorry, Snell's law is always with respect to the vertical, or always with respect to the normal. So let's draw that briefly here. So that would make this 90 minus 55. So that's 90 minus 55. So that's important to note. So that's going to be actually 35. So let me just say 35 degrees there, and then we can find theta water there as well. So we kind of know the trajectory, the aim of all of this. Now, where does this leave us? We need to find physical distances of the shadow, right? So here, I'm going to say the distance of the shadow. This is where you have to get creative with your geometry. The distance of the shadow, well, is going to be a combination of this distance plus that distance. Now, the first distance, I think we can measure without even using Snell's law, quite frankly. That distance is going to be given by the same as this distance in here. And that distance is simply one of the sides of that triangle. So let's call this, we got to label these things. Let's call this distance 1, and let's call this distance 2. So distance 1 is going to be the adjacent side of that triangle. So we have the opposite side, so I think we're going to need tan. So this is the opposite side, this is the adjacent side. The angle is 55 here. So I would say D1 is going to be 50, 10, 55, I believe. Opposite, nope, let me just not, I don't think that's right, hold on. Tan of 55 equals opposite over adjacent. Yeah, I had that wrong. So that means D1 is going to be 50 over tan 55. Okay, so there you go. So we have that distance. Boom, we have that one. Now we need to find out what distance 2 is. Well, we know the angle well, let me draw the triangle. So now for distance 2. Now for distance 2. The triangle that encompasses distance 2 is this. And we know this angle here is going to be theta W. Right? We know what theta W is from before. Now, here, going through it, we need distance 2. So that's going to be, again, tan. So it's going to be tan of theta W equals opposite over adjacent, which means distance 2 is going to be 150 times tan theta W. And we have theta W from Snell's law. And then that will allow you to calculate distance 2. So that will allow you to say, we now have distance 2. And then, of course, the total length of the shadow is going to be the sum of distance 1 plus distance 2, which we have. We have both of them. So it's going to be 50 over tan 55 plus 150 tan theta W, whatever value theta W happened to be. Okay, So a question that seems benign is a little bit more involved than perhaps you may have expected. And you know, you're not needing to pull in other chapters of physics, but you are needing to know basic math. You know, manipulating angles, compound shapes, stuff like that. Okay. Now, this is the last question that I have. This is an example of an infinite universe. Oops. But I don't think doing the problem will really illustrate, I don't think doing the problem numerically will illustrate what I mean by an infinite universe. The only way to really get a sense of an infinite universe is to, you know, try to do it yourself at home, because you can easily do this at home. So what I would recommend doing with this problem is, you know, you can review the solution. The solution is posted here, but try to do it yourself at home if you are able to. I mean, some of you have only one mirror or something like that, but if you are able to sort of stand in front of a mirror, so let's call this like mirror number 1, and let's call this mirror number 2. If you're able to have a mirror behind you and a mirror in front of you, you can actually see the back of your head, which is kind of really cool, because the back of your head, you know, is shining light into here and then reflecting this way and then back into your eyes like this. And then it keeps going back and forth like that. So you see the back of your head, but then you also see the front of your face even behind you, and then you end up getting an infinite amount of parallel, quite literally parallel universes behind you. So it's cool to look at. It's not so cool to just study, because it's a pretty boring analysis and it doesn't really pack a lot of punch. So I've put the solution here for you, so you can still try it at home if you'd like. But I would really like it if you could try to mimic this at home. And I think that's really going to blow your mind at home. And again, when I teach this class in person, I am able to do this for students. You know, I hold a mirror behind them and I hold a mirror in front of them, and then whoever's interested can come up and look. But unfortunately, we're not able to do that here. So it makes teaching optics very difficult when I'm not able to show you the optics. All of optics is literally sight and optical illusion. So it makes it very hard to teach optics effectively when we're not together in person. Okay, anyway, so that aside, hopefully those examples helped a little bit in conjunction with the double lens example of using the thin lens equation. So we're going to call this a wrap for the geometric optics chapter. And I will pause the recording because we're going to start the wave nature of light, well, I guess next. So that should be a different video. But in between videos, I'll pause and I'll take any questions that anyone may have. So I will see you in the next video.